I'm going to do a short example of plotting the Fluconazole equilibrium on a Sillen diagram, and this is the equilibrium that's used in example 18.4. The problem, the example 18.4 does not require the Sillen diagram, but there's a couple steps that are helpful for you to see, and it's helpful for you to see that perspective of how the diagram would be created for this particular equilibrium. So in the problem statement of example 18.4, we have an apparent concentration of 1.5 times 10 to the minus third, and we can figure that we can calculate the log of the concentration then is minus 2.82. And because this is a fixed apparent concentration, all the fluconazole species will always be, the sum of all the fluconazole species will always be this concentration. And so we can find that value on our axis here, and we kind of know that that's where our horizontal portion of the equilibria will occur for this fixed apparent concentration. The problem asks us to look at the effect of pH on the equilibrium. Now the problem statement gives us the reaction here, and when you look at the reaction, recognize first that it is a reaction of the base because hydroxide is being formed. Now our convention is always to plot on a Sillen diagram in the acid form. So we're going to have to convert this equilibrium to the acid form before it is plotted. And the problem statement gives us the log of K, but it does not explicitly tell us that it's the base form. We need to recognize that. So I've taken the equilibrium relationship and I've calculated the log of K from this equation, recognizing that it is the base form. And that provides me then the value of the natural log. Now for the Sillen diagram, I need to work in common logs. And pH values are based on common logs also. So I've done that conversion here, and you can see the log of the common log is of this equilibrium constant is minus 12, which gives me a pK of 12.2, and I can then convert that to the pKa value, knowing the pK of water is 14, and the acid and base forms need to add up to 14. So by difference, I find that the pKa is 1.8. And I can also calculate the equilibrium constant value then. Now I need to express the equation in the acid form in order to write it on the Sillen diagram, construct the Sillen diagram. And so I've done that here. I went back to the original equation that was given, and I recognized what was a base and what was an acid. And after I've recognized those, I can write the acid form. So I can take the acid form, reacting with water will provide the base form and hydronium. Okay. But now I'm ready to plot this on the diagram, and I no longer need to work with the equations directly. I'll work with the graph that represents the equations. I know the pKa value is 1.79, and I know the apparent concentration is on the log plot is going to be minus 2.8. So I find the coordinates for 1.79 as the pKa and minus 2.82, and I'm going to go down 3/10 of a log unit on the log scale here, and that's going to be my construction point, and I'm going to go about a pH unit away on each side. I'm going to draw a horizontal line on either side, okay, about 1 pH unit away. Then I need to construct the diagonals. I've got one proton here that's going to be involved in the dissociation. And I want to do this relative to my original construction point here at the pKa. And I'm going to do that quickly by going over 1 pH unit and down 1 concentration coordinate here at a time. Okay, and I do the same thing on the other side. Okay, and then I'm going to get a ruler and I'm going to construct the line. I go close, about 1 pH unit away. All right, I'm going to do the same thing on this side using my original construction point, and I'm going to hand sketch in the curve that goes through here. And this becomes the equivalent construction on the Sillen diagram for fluconazole. And I can label this, recognizing that the acid with the proton on it is going to be over here, and for this molecule it happens to be that it's the charged species. You can't tell from whether it's charged or not whether it's acid or base. You have to look at the reactions and where's the acid, where's the proton going on, where's the proton coming off, what's forming a hydroxide, what's forming a hydronium. And so the fluconazole neutral molecule would be over here. Now remember the meaning of these points. This point is 3/10 of a unit down here, and this is where the two species of fluconazole cross. And so therefore this is the point where there's a 1-to-1 ratio of the two fluconazole species. At the pKa is where there's a 1-to-1 ratio. Okay, and we go 1 pH unit away, and over here we have basically a 9-to-1 ratio. Okay, we go 2 pH units away, and we have a 99-to-1 ratio. Okay, at this point. Okay. Hope that's helpful. Thanks.